There are a ton of applications for this, as you can imagine. For the sake of time, I'll skip over this, but anything from pre-processing face recognition to morphing into your favorite avatar for digital effects and makeup removal, et cetera. It's endless. You might be wondering, isn't this an old problem? Isn't this solved? No, it isn't solved because there's a lot of difficult poses we still cannot handle. But for many years, it did calm down. There was a lot of people not working on it. Why has it got a lot of attention lately? Because of deep neural networks are now in the picture and we're using them for detection. So we're pushing the state of the art on ever so difficult data sets that we never thought were possible before. So again, given a phase, we pass through a deep network, we get our landmarks. So the way that we formulate the problem is we have this heat map that comes out. The heat map is, for each of the landmarks, we then translate, as you can see here, a heat map for each one of the landmarks. These are all superimposed. We translate, we find the maximum to a coordinate. However, to do this, we need a max. A max is not differentiable. We couldn't train end-to-end. So previous works has used a soft argmax, which essentially finds the expectation over the 2D space. So it finds the expectation, it generates these heat maps, quite smudged, as you can see, not very high in precision. So we thought to ourselves, what do we want to do? We want a practical system that works well. This is state-of-the-art as of 2018 CVPR. But those heat maps, how can we improve these? There's not enough statistics here. Why don't we add variance? So we took and we actually, the soft argmax, the way it's formulated, we used that as our expectation, found the deviation from that mean, standard deviation from that mean, and we ran a KL divergence on it using Laplacian because of its peakiness. A lot of details I'm scamming, but as you can see here, our loss function finds much more distinguishable landmarks. They're nice and tight, confident. Let's see if the precision translates to accuracy. And again, this is the model. There's a lot of parts I'm going to skip over because it's not really the meat. This was an adversarial aspect. As you can see here, we beat, look at this number because this is without the adversarial. We beat state-of-the-art by a margin. We do zero data augmentation. We have a vanilla network. We do no data augmentation. We do no training tricks because my advisor at Snapchat was adamant about how we just want to show the loss. We literally do not even do no data preparation. So we push this a lot higher currently. That's down to 3.6. So as a last experiment, this is why I chose this one, is we just took our network. If we go back here and look at a network, it's just a bunch of stacked layers that have a number of channels. We just started reducing the number of channels by factors of 2. We go here to the the second column of numbers, and you can see we still compete with state-of-the-art at 160 kilobytes of memory in real time on a CPU. This is doing nothing but just dropping filters, no training tricks, nothing, just dropping filters. So it's a very stable loss function. You can see how precise these are, how precise our landmarks are that we're predicting from. Some more samples, qualitative samples, showing how precise it is. And if there was time, I would blow into beards, and arguably we were actually closer than ground truth. Having a beard, they're kind of off a little bit. We use this on hands now. We just applied this to hands. I did not have this at the time of the paper, the poster. I did have this, but not time to put it in. We're doing it on 3D faces now. This loss function is generalizable to anything with landmarks. 3D faces. We're doing with human poses. So this literally is taking the place of any encoded, decoded-like structure that's trying to do landmark detection. You can see that we could run it in real time, just on video here, showing in the GIF. What's next? I honestly just want a single network that pushes out hands, body, and face, period, just all the landmarks for biometrics, a single network that's using our loss, focusing on the different aspects, and maybe add some quirks like attention and some other neat little tricks that can make it better for practical purposes, because at this point, the loss function's proven to be effective. So I think it's time to soup up the network a little bit. Many thanks. And I'd rather discuss. That's why I kind of wanted to rush through that a little bit. So I'm going to go ahead and, how do I? Yeah. Can you guys see me? I'm open for questions.
Joseph, very impressive. Very good stuff.
Thank you.
How
ICCV actually, if you want.
how um, how accurate and how much confidence can you put behind some of the labeled points for non-visually apparent um, um, uh, non-visually apparent sections, such as a person that's turned their face? It appears like you're labeling, say, the backside of the jaw when that's not actually visual, like visibly constrained. How accurate do you think that part of the model is or could be?
Very interesting question. And that's funny that you noticed because that was on the second set that kind of went through quick. The first set, we didn't have that because that was on 2D. So that was applying 3D learning to the 2D imagery. It's hard to really tell. We have hand-drawn ground truth that they labeled AFLW with the 3D points using the model. We do very well on it. So according to that ground truth, yes, but that is, again, a 3D model applied to 2D. It was kind of a stepping stone before we went to the 3D faces.
Yeah. Okay.
So it, by the looks of things and looking at qualitative results, it looks like it works very well. Actually, I think arguably better than ground truth sometimes, because if you know faces and landmarks, they're not accurate labels. Every time it's different.
Yeah.
So, I mean, sometimes I want to, I'm sure it goes both ways, but a lot of times I feel that I should have more points than I do looking at the comparison, especially with kids.
Do you feel like you have a large enough data set? I mean, are you able to use some of Snap's data?
Here's the thing, that's the piece I skipped, is we use minimal data. We use adversarial learning, and we did it in a way where we use just because the abundance of free images on the internet faces, we just grab MegaFace, a very unconstrained data set. It's quite unconstrained. It's in the wild, more so than any data set we're doing landmark detection on. We use that to make it show that we're really taking it from the internet. And then we did adversarial training with only 1,000 training samples with labels, and then 70,000 adversarial. So we did that in an adversarial manner, and we're able to boost performance the more images we add. Our loss function is the only one that does that, because otherwise it's always fooled. It never gets fooled. Our loss function is the only one that can actually stabilize that GAN training. And no, we didn't try it because our goal was to leverage minimal data. The story goes backwards a little bit, because that was our research question. And looking at the soft argmax when we implemented it, I'm like, we're like, this is not the most precise heat maps. And then we went to the loss. So we got to the loss that way.
Interesting.
So yeah, and we did, like I said, no data augmentation. When we add data augmentation, which I probably should have thrown up the numbers, like I said, like it drops down to 3.6. And the 160 kilobyte drops down to 4.2. And that's with no training tricks, just data augmentation. So we still can add attention. We still can add, schedule and learning rates. We do none of that. It's a very fully convolutional connected network, just encoder decoder, dropout ReLU, leaky ReLU.
Interesting. Very interesting.
So it is all about the loss. If you look at the paper, we put it actually in bold that it is all about the loss. We use as simple as a network as we possibly could to show how effective this is. And we beat the state of the art that are using millions of types of images from augmentation, whether it be NVIDIA's work or it be the work with the style detector, all the different style pieces.
Great.
So the real great piece of this is the fact that we haven't even explored MobileNet, or we haven't explored any of these tricks to make a smaller network powerful, accurate. We just drop layers. We literally just drop layers. We're at 160 kilobytes. That's lower than the MobileNets that you're hearing of state of the art. And it's running in real time on a CPU for near real time, 22 frames per second about. We have not even optimized for that. So once we go in there and start digging in, there's so much room to play. There's so much room to make this improve on this. At high practical value, I feel, both in terms of its robustness, in terms of it's being lightweight and working well, and it's dynamic manner in which you can use all these different types of data, all of, like whether the hands, the faces, the bodies, all that will be in our PAMI. But I wanted to share with you guys first. So it's not, that stuff's not published, but it is in the process of being published. Because it's out of
Can I ask a question?
Yeah.
This is not my technology area, but I'm very impressed. But I'm in the bio field. But is any of this applicable outside of facial recognition? For example, I know from some patents that I've worked on that people are trying to do analysis of tissue samples, for example, to analyze whether a slide is cancerous or not cancerous. And for the most part, they're using AI to do that. So it just seems to me that perhaps some of these principles
That is another great point, and
be
it's
applied
something.
in that area as well.
Oh, sorry, you broke out. I didn't mean to interrupt. So yeah, no, that is a great point, and that's actually something that has been on my mind quite a bit. So you say like biomedical imaging, detecting that anomaly, or segmentation of different applications, trying to find detection of different types, and they use what soft augments a lot of the times. They use that first loss that I had shown very briefly. This is really building on that, so absolutely this could be used. Have I tried it? No, I would love someone in that domain to work with to do this, but I think it would be a matter of honestly plug and chug and find the right parameters. It's a generalizable loss, because it was kind of like going from k-means to your Gaussian mixture models. Literally, it's actually a direct almost comparison. We added the variance to the loss, and we essentially we allowed for a little bit of freedom, and that accounts for the noise in these labels, which we can tighten. We can go into sub-pixel space if we're to do biomedical very easily, which we have done, got better, more precision, but that's for faces, you want that wiggle room to the noise. But something like biomedical, go sub-pixel space, absolutely. That would actually make it a proper probability.
Well, I mean, one advantage you might have is that in order to do this by AI, you need a very large set of images that have been characterized, usually by a pathologist, and that's hard to get, and you have to collaborate with somebody to get it. And there are certain hospitals that have these, databases of tens of thousands of these images. You probably don't need all of that data to apply your approach, and so it probably would be a lot easier to investigate and to make work than an AI approach.
Yeah, I would be certain that would be a very interesting research area. See if we can get that adversarial component working on something as something so something of the medical domain that's so precise and so particular, and often an anomaly, I would think. But again, I'm no expert there. That would definitely be an interesting research question. And our discriminator was very strong with that loss. We could have kept going. We could have kept adding more images. So it does, our loss learns quickly. It takes a couple of iterations. So that's really why that works. Because otherwise it just gets full. It's just like, okay, we know you're fake. It doesn't actually add anything to the gradient because it doesn't work. It doesn't fool it. But ours learns quickly. So right away, it's like, wait, we don't know if that's real or fake. And then we're getting boosted in our gradient. And that is the key. That quick, like after 2 iterations, our heat maps are pretty tight. They do get tighter. But it's like, wow, after 1 or 2, and then after 100, we only do 120 iterations. Because again, my advisor was all about no pushing it to the limit. Let's just show people what it is for what it is. And it was a very hot hit actually at CCTV. I was very actually surprised. My first time at a big conference like that, and like I was flocked, and people were like, oh my God, a real science research paper. I'm like, I don't even know what that means. I feel like everyone has one, but thank you. Like that, but it's great because people email me all the time about this, and they're starting to, even PyTorch wants to extend soft augmax to have the KL divergence, which I kind of want to change the name of because you can use any divergence. I just did the JS, anything that matches distributions, and that works actually a little better. And Gaussian in some cases works better. So I think the name's too specific, but the loss in itself, that's semantics. It works quite well, and you can use different distributions. You can use different divergent functions or probability matching. And we've tried it, and it's going to be in the PAMI, and it works well. we push state of the art. I really don't want to be bragging too much about what I can't show right now, but we pushed state of the art quite a bit when we started playing around with that stuff. When I got back to my lab and started being able to just run all different kinds of tests, different distributions, different probability matching functions, it really made a difference. We had 2 weeks at the end of the summer. We found this and we rushed to do it and then we added it to the adversarial component. So I went back and I played with that loss, and that I feel like that is, again, that's why I wanted to present that when this is not even the core of my thesis. Core of my thesis is actually a different phase topic entirely.
Great. Very cool stuff. Very, very cool stuff.
Yeah. Thanks a lot.
Thank you. I appreciate it very much. Thank you guys for staying extra late. I know there's probably been a day. And any of that medical stuff, if you if there's anything you can connect me with, anyone you can connect, I'm so open.